just in case the title wasn't strong enough, I thought I'd highlight the two important points from an applied geneticist perspective. So I'm often on the road for cattle, dairy, beef, or sheep, and you're talking to farmers, and you're trying to get them to adopt these type of technologies. And for the Illumina people or the Affy people or any service provider in the audience, they're well aware that before I even say hello to them, I'm asking them what's the cost of the chip and what's the cost of doing the actual service. I'm a bit of a prostitute when it comes to genotyping. But of course, it's not just all about cost, it's also about information content. So if we look at the practical applications of genomics, and most people here, especially being the WC GALP, are interested in deriving more accurate estimates of genetic merit of an individual. And that's both for candidate breeding animals, but from an Irish perspective in particular, where we have a lot of crossbred animals, both in cattle and in sheep, we're also interested in deriving genetic merit for commercial animals. Also, when you're going to a sale, and again, we heard a bit about this yesterday, I'll talk a little bit more about it, is when you go to a sales and you're purchasing a ram for a significant amount of money, you want to be sure that that sire of that ram is actually truly that sire, and similarly with the dam. And at the end of the day, most people here are interested in genomic selection, so deriving genomic breeding values, but not using markers like marker-assisted selection, but actually using it across the entire genome. So a large number of markers, be they SNPs or indels or CNVs. And then major genes is obviously also important. As much as we'd like to think that farmers are interested in EBVs or EBVs or PTAs, whatever you want to call them, the vast majority of commercial farmers, like it or not, aren't really that much interested in genetics. They're still interested in looking at their animals and selecting them based on the shape and the size, etc., and looking at lineages. So how we're selling genomics, and not just in sheep, is actually the correct parentage assignment. It's getting the parentage right. So again, when you go and purchase your ram, and we rather than telling farmers their EPDs or their EBVs, whatever you want to call them, we branch them into stars. So a 5-star animal is in the top 20%. So if the ram is wrong, the 5-star animal that you paid several hundred euros for could actually be a 1-star animal, right? And you'll see in a second that 10% of the time, the parentage is incorrect, right? So it's resolving those. Another thing, and again, if people here are dealing with particularly beef farmers, they have this phenomenal fetish with major genes and myostatins. And our sheep breeders have a complete fetish with scrapie. They don't know how they're going to use it, but they want to have scrapie results. So having scrapie on a platform that consistently works is key for uptake. So we actually don't sell genomic EPDs to farmers. We actually sell that they get their parentage and that they get their scrapie results. And the byproduct is they get more accurate genetic evaluations. Our goal, and again, this isn't just in sheep, is to actually genotype every single animal in Ireland at birth. And that's commercial and breeding in beef, but predominantly breeding animals in sheep. And this will allow us to generate a genomic reference size. So at the end of the day, and it was on the title of my talk, it all comes down to the return on investment. What can farmers pay for any type of a technology which will give them a return on investment? And you can see some very, very simple maths. Brendan Robertson's equation here, delta G. It's a function of the intensity of selection, the accuracy of selection, genetic variability, and the generation interval. So really what we're altering here with genomics, in sheep in particular, per generation interval isn't as bad, is the accuracy of selection and the intensity of selection. So this is the maximum cost, and I haven't put it in the actual value from an Irish perspective because you'd be a bit shocked because it's a very low profit margin business. But if you were to select from your replacement females, none of your replacement females, so you do no selection, well, actually there's no value of doing genomics then, because from a more accurate EBD perspective, because you're selecting every animal. Or you're selecting no animal. If you're selecting every animal, it's exactly the same. So the maximum price you can pay for any type of genomic technology is maximized when you're selecting 50% of your animals. But of course, if you increase the training population size or you become a better geneticist, you can increase the accuracies of genetic evaluations. And as you increase them, then farmers can pay more and more for this technology. And of course, this mathematics is really only relevant from a genetic gain perspective. There are other benefits like inbreeding, etc., and mating advice. So that tells us how much we can actually pay our individual Irish sheep farmers or any farmers can pay for this technology. These are not actual costs. These are just example of costs. We've done a lot of tendering in many different species, and I'm kind of pulled out some of the best that you would get in such a situation. But sample procurement is probably around €1.50, so getting the tag. And we would do it where it's fully aligned with the national identification, so you have full and unequivocal traceability. So it'd probably be a bit more expensive than other services. DNA extraction varies obviously, but it's usually around €1. The chip, again, that's only a look at across what many chips are now in cattle and sheep. Genotyping services around €5, and then a service charge of 10. But the point I want to make, and it's a point that Andre Egan made to me several years ago, was that we are always bashing Thermo Scientific or Illumina to drop down the price of the chip. But the price of the chip is really only around half the price of the rest of the service. So there are other parts of that service that we can also improve, in particular the sample procurement and the genotyping, I think, and the DNA extraction. There are room for that as well. But from a price of the chip perspective, it's volume driven. Anybody that does any bit of volume would know that the price of the chip reduces considerably as you increase the number of genotypes, and also the number of SNPs. Used to be an issue, not so much of an issue anymore. So that's the kind of the costs, the return on investment. Now, what's actually the returns? And again, many people here would focus probably on the blue dot, which is your genomic evaluations, trying to generate more accurate EPDs or EBVs for farmers. And again, those of us that work with farmers know in our hearts of hearts that really, with the exception of probably the dairy guys, they don't really use them all that well. Right? So there are many other uses, and this is again how we would sell a lot of our genomics, is the parentage, the traceability, monitoring lethal mutations or congenital defects, looking at mating advice, karyotyping, I'll talk a little bit about that, and breed composition. The one in orange is the one I think is going to come into the future, big time. We're already doing it unknowingly. So you rear, in beef, for example, you rear an Angus animal very, very different to a Charolais animal. That's precision genomics, really. You're managing the animal based on its genomics. I just put this slide in here because it came up a few times yesterday, I think, with the French. What is the parentage issues in France and the other countries? So this is just some examples. So this is a bit of an old slide, but at this time, we had 13,000 sheep genotyped. 5,000 of them also had a parent genotyped. So if we look at our incorrect sires, and these are all breeders now. So these are the guys that are selling these 5-star rams to commercial farmers. 10% of the time, the parentage was incorrect. And our flock size is like, I don't know what it is on average, it's probably around 20, right? So there is still a phenomenal amount of errors inside there, okay? From a dam perspective, what you would think would be a lot higher, really, is 7.6%, right? Combined, 2% of the lambs had both their sire and their dam incorrect. So this is really how we're getting genomics adopted in our industry, is actually predominantly on this statistic. So that when the farmer goes to the mart or to the auction, what he's buying is actually truly, the parentage is truly correct. And you can go onto our national website and you can look at the individual animals. In this case here, you see this animal here, its sire is genotyped and its dam is genotyped, and it's 100% matched. So again, for the cost of genotyping, which I'll talk about later, but it's sub €20, this ram should be able to command at least a €20 higher premium in the auction, right? So it's minimal cost, but being able to put that on your stall and say this animal is 100% parentage verified is a huge benefit. So when building the chip, looking at the characteristics, obviously it must be accurate and informative. For me, as I said, I'm a bit of a prostitute. I don't care. Is it Illumina? Is it Thermo Scientific? It must be agnostic to the vendor. And again, I'll talk about this in a second. I must be able to move as the price comes down. And it's exactly the same for the platform or for the service providers. JR from GeneSeek or Romy from Weatherby's, I should be able to move, and it shouldn't make a difference to my genotype. Like George had a talk of 30 different chips in his platform. Again, George, just all the data should just come in. You shouldn't care who's sending you that data. Must be flexible, so I must be able to add chips. Again, we saw a talk from France on the HH7, the Holstein new haplotype. We need to be able to add that straight away into our platform, right? And it must be BRCA and cross-compatible. So the characteristics for me, it's as few as possible to keep the cost down without losing information. High quality. So again, we can talk about some of the old chips, some of the first chips that were launched. They were 50K, whatever, but when you did the editing, you were down to around 38K. Right? So you were losing already 20% of your data. They must be repeatable within and across platforms. So again, what I'm saying here is you must be able to move from a low density to a high density and get the same genotype for that animal. You must be able to move from GeneSeq to Eurofins to Weatherby's, get the same genotype, and you must be able to move from Affy or from Thermo to Illumina and get the same genotype. It should be irrelevant. Excellent call rate, and of course, informative of crossbreed and within-breed minor allele frequency. And I'm just giving an example here because I think this is not often always done correctly. So many people would look at the minor allele frequency of crossbreeds, right? But in this case, you have this animal or this breed who is all big A, this breed who is all big B. If they're equal quantities, the minor allele frequency is 50%, but it's not really informative. The minor allele frequency in this breed is 0, and this breed is 0. So it's really the within-breed minor allele frequency. From an imputation perspective, it's scattered across the genome, and when I was building the 11K, what we looked at also was going into the areas that were had poor imputation accuracy, and just really kind of saturating those areas with some SNPs, just to improve the imputation accuracy there. Representation of the sex chromosomes, I think of the 12,000 animals, 64 of them had the incorrect sex. So we must be able to tell the farmers that. I think they already knew, but tell them that they made an error in recording it. International parentage panels must be all represented on it, and again, representing the major genes. So I'm just going to go through a lot of these individually. So if we talk about the repeatability, and this is just some work, this is exactly what happens when you don't have good systems of recording things. You end up genotyping the same animals twice by accident. I could, of course, pretend that we did this purposely for this study, but in reality, what we did was we ended up genotyping 25 animals on the Illumina 50K twice, right? And the good news is that the genotype concordance was 99.9%. So as you would like to expect, exactly the same genotype with exactly the same panel. Then we also somehow genotyped a different 21 animals on the 50K and also on the Illumina LD. These are actually with different service providers as well. Again, more or less exactly the same genotype, irrespective of the chip or the service provider. And actually, we designed this one where we genotyped 84 animals on the Illumina 50K and especially built Affymetrix 50K as well. And the concordance between them was very high, 97%. But when you limited it to just the high quality SNPs, so those that were scored very high quality from the Affymetrix algorithm, it was 99.9% or 0.5%. So our conclusion was that really it didn't make a difference. You could move across these platforms and the concordance rate was good enough to put the two of them together and use them in any type of analysis thereafter. So when we look at, well, originally, and some of you might have heard the talk in ISAG, built an 11K Axiom platform. How I chose those SNPs were they had to have high quality. Those of you that are familiar with Illumina, they have this statistic, this Gen Train score or GT score for the quality of the clustering. So they had to have good clustering ability so we could differentiate the homozygous from the heterozygous from the homozygous. Had to be excellent repeatability based on the last study. So had to be given excellent concordance between if it was an Axiom platform or an Illumina platform. Excellent call rates, high minor allele frequency within breed, so it had to have a minor allele frequency of at least greater than 5%. We're scattered across the genome, as I said, saturated is in areas where there was poor imputation, and representation of the sex chromosomes, parentage panels from several different countries, and the major genes. That was an 11K, but in the past few months, Thermo have actually added significantly more SNPs to bring it up to a 52K. There's actually more probes in that. I think there's around 60,000 probes targeting individual SNPs that we thought were important because there are, most notably, the Scrapie. Any of you that have worked with Scrapie would know it's a difficult enough. Well, some of the markers are difficult enough, so we put on many probes on the platform just to be sure that we got Scrapie because it was so important. Well, it's apparently so important for Irish farmers. And the good news is we got it to work. So if we look at genotyping quality from a quality perspective, so again, those of you that work with Thermo or Affy would know these kind of quality scores. So polymorphic, high resolution is where you get really good quality clusters. So those of you working with Illumina, these are the high GT score SNPs, right? What you can see is this is the representation within some of the animals that we've done. This is a relatively small population. We did have some DNA quality measures of those samples at the time. So this is probably an underestimate, but 77% of the SNPs fitted within that category. So we're getting very good quality data from this platform. From a call rate perspective, you can see here, this is just a histogram of the mean call rate of the 50,000 SNPs on the platform, the percentage. You can see obviously a huge density here, whereby the vast majority of them had an exceptionally high call rate, and they were chosen to be such. Okay, so that really is no shock. Looking at the extent of segregation, and here's just looking at some Irish breeds. So here we have the Belclare, the Suffolk, the Texel, the Charolais, and the Vendine. And this is the minor allele frequencies, or the proportion of SNPs fitting into each bin of minor allele frequency for each of the breeds. Again, remember, we chose these to be highly polymorphic, especially the ones that we were interested in. You can see that the vast majority, there's very few monomorphic within breed of those particular SNPs. Okay, and the vast majority of them are highly segregating across the different breeds. On the 11,000 SNPs, we also did something, Hans Datweiler and Iona McLeod ran them on some of the Australian breeds. I can't remember what they were now, but they were also segregating to a very high extent in those breeds. This is just the number of SNPs per chromosome, and the red is from the original 11K, and this is onto the new 52K. So again, you can see a good representation of the chromosomes, or the SNPs on each of the chromosome. And then major genes, this is just Scrapie. There are several major genes, I've just shown a few. Scrapie is very important for us, and this is one of the dibbles that's really hard to get working on other platforms. But you can see he's clustering very, very well on the Affy, or the Thermo, I keep calling it Affy, sorry, on the Thermo platform. We have validated the Scrapie on a relatively small number of animals that were also genotyped by GeneSeq, and we're currently in the process, hopefully the data is coming tomorrow, to validate it even further. Okay. This is kind of a pet project of mine, so I said I'd throw in one slide on it, and this is looking at the karyotyping. So looking at the intensity of the alleles to actually get a measure, so we know we do this for copy number variants, but if we look across the entire chromosome and we can see that the allelic intensity is particularly low, then it looks like it's monosomy, you're missing a chromosome, or if it's particularly high, then it could be trisomy. So when we're just scouring the database, I was actually working with John McEwen and Ken Dodds on this. We found this lady here, our PhD student calls her Tina Turner, so she's a Turner female. She's a female, this is her actual karyotype, we got it done. She actually, as I'm sure most people know, females should have 2 chromosomes. She only has 1 chromosome, so she apparently is infertile. Interestingly enough, she had a twin. So after driving to the north of Ireland to pick her up and driving back down, the farmer then rang me 2 days later and said he had a twin of exactly the same, of the same mating. It looked exactly the same, so I had to drive all the way back up again and pick up the other one. The 2 of them were non-identical twins, so they shared the correlation of 0.5 between their genotypes. And apparently, from what I can gather, and we had a very good reviewer, and he confirmed it, that this is the first ever non-identical set of Turner females in any species. But in a nutshell, what you can see, and this is irrespective of the platform, we actually genotyped the animals with Illumina and with Affymetrix. And what you're looking at here is the intensity of the X chromosome. These are all your females. Here is your Turner female, right? And actually, if you look at it we didn't genotype any males on the Affy, but if you look at it from the Illumina perspective, these are the males. So the males obviously have 1 chromosome. You can see that one female, and because she has a Y chromosome, or you knew because she didn't have a Y chromosome that it was a female, she actually has the same intensity, allelic intensity from her X chromosomes as the males. So in other words, she only has 1. Okay. So just to conclude, in case you haven't got my point, low cost is key for us, irrespective of species, especially in sheep. It's an extremely low margin business, actually is a negative margin business. That's the advantage of being in the EU. They pay you to be unprofitable. So excellent quality genotyping is also important. Highly reproducible. Again, I need to be able to move across service providers, across platforms, across vendors, and get exactly the same result. And that's quite clear to me now, or that's very clear to me now that that's what is being achievable. Highly informative markers, so imputation to high density, especially in sheep. We heard some talks yesterday about the LD being weaker in sheep than what I'd be used to, particularly in the Holsteins, and to lesser extent in the cattle. Traceability, parentage, and breed composition. One thing that we haven't done a huge amount of work in sheep yet, but it will become big, is co-ancestry, estimating co-ancestry amongst the animals in the flock, and mating advice. And again, those of you that were in Tara Cartley's talk about the sire advice from the dairy, it's all based on using genomics to identify the least related animals, so you can advise on matings, karyotyping, and major genes. And then it's particularly from a thermal perspective, it's the ability to alter the content very, very rapidly and guaranteed that content. So if I want to put a SNP or an indel or any sort of a structural variant on a chip, firstly, I have the ability to do that and do that rapidly. And secondly, I'm guaranteed that I'm actually going to get a result. Okay. The final point again, and again it was a thermo issue, was particularly from the scrapey perspective, was the support in actually the design of the probes for a lot of these challenging SNPs. The other final point, and maybe I shouldn't say it, but it is important for the likes of George, anybody who deals with any bit of genotyping whatsoever, is to have that data coming in exactly the same format. And like it or not, Illumina were first off the blocks. A lot of us bought Illumina in the different species, but the format of the output now from Affy is exactly the same as Illumina. The final report file has that 11 rows at the very top and exactly the same columns. So it can be easily implemented within the pipelines. Thank you.